Okay, for this second talk, we welcome Marina Ferreira. She will talk about localization in multi-component coagulation systems. Please.
Thank you, and thank you for the invitation and to the organizers for this very nice workshop. So I'm going to talk about joint work with Jani Lukkarinen and Sakari Pirnes from Helsinki, Juan Velázquez from Bonn, and Alessia Nota from L'Aquila. And on multi-component Smoluchowsky coagulation equations. So I'll start by presenting the particle system. So we are interested on studying a system of particles where each particle is characterized by a vector. The vector may contain the sizes of different components of the particle. So if we think about particles constituted by different chemicals, for example, then each component would be the size of the chemical. And the particles may merge to form a new particle with a composition given by the sum of the two compositions. And this happens at a rate that depends on the composition of the merging particles. So it's encoded in this coagulation rate kernel. This may depend on the background medium where particles move, or yeah, and that's it. And so we are interested in studying how the particles grow and how their composition changes. This is motivated from applications from aerosol science and also polymerization or astrophysics. They have been using these models to study the formation of Saturn rings, for example. Okay, so since we want to study a large system, we consider a description of the density of particles with composition X. And X is a vector with positive or non-negative coordinates, and the density is evolving according to the Smoluchowsky coagulation equation. So this this is an integral differential equation given by the time derivative of F equal to the coagulation operator. The coagulation operator is divided into a gain term and a loss term. So the gain term is due to the collision or coagulation between particles of composition X minus Y with particles of composition Y, which produces a new particle of composition X. And the loss term is due to the coagulation of particles of composition X with any other particle in the system. So the 1/2 is because to remove the symmetry in the collision. Okay, so then this equation has been studied mostly in the one component case for d equal to 1, where X represents usually the size of the particle, and there have been many results on existence, self-similar solutions, mass conservation by several authors. So this was proposed in 1917, and since then there has been many results. There are still some important, not well understood questions, like the long time behavior. It has been characterized only for the so-called explicitly solvable kernels. So k equal to 1, so the constant kernel, the additive kernel k equal to x plus y, or the multiplicative k equal to xy. Otherwise, there's no good theory. There have been also works on the derivation of this equation from Brownian particles or from the coalescence processes, but so this has been obtained for specific kernels. In general, there's also a lot to do. And what we are studying is multi-component equations that have been not so studied before. So I just want to give some properties of this equation. So this equation has a mass conservation law, provided the integrals converge. So for certain coagulation rate kernels, one can obtain this that the first moment of the solution is conserved in time. So just by multiplying by x and integrating, we obtain this identity. And associated with the mass variable, we have a continuity equation where the mass flux is given by this double integral here. And this leads me to define different types of solutions for this equation. So we can either study a closed system where particles just merge to form bigger particles, and we study how do they grow. So in this case, we have mass conserving solutions. Or we can consider solutions for open systems, so where we allow input of like very small particles, like modeled by a flux boundary condition. So by adding this boundary condition, we obtain solutions with increased mass, so the mass will be increasing linearly in time. For if this J0 is a constant vector. And these solutions are expected to approach to the stationary solutions, which correspond to solutions where there is input through 0 and an output through infinity. So what happens is that for some rate kernels, it's possible to have a balance between input through zero-size particles and output through infinitely large particles, which allow then the existence of these stationary solutions with constant flux. Another way to see this behavior is to consider the equation with source. So I will, in a minute, show some results on stationary solutions with source and also mass conserving solutions. So yeah, here is a bit of the literature on these different types of solutions. There has been much more in these mass conserving solutions and in the rest. And I'm presenting recent results on multi-component mass conserving solutions and stationary solutions. So as we will see, they will both have a similar property that we are calling localization. So, okay, so let me start with the stationary solutions. And in 1996, Krapivsky and Benaim, they obtained the explicit solution for the discrete multi-component coagulation equation with constant kernel. So here, instead of integrals, we have sums, and alpha and beta are vectors in ND. And in this case, we have the equation with source. So this source is supported on the monomers. And they obtain an explicit solution for this equation using generating function. And then they show, they present an approximation formula for large sizes. So from this formula, we see that I have here the plot of this shape, and we see that for large sizes, most of the mass of the solution is supported along in a region near the line defined by alpha 1 equal to alpha 2. So here I'm representing the case with two components, d equal to 2. And this should be alpha 1 and alpha 2 and alpha, okay? So we see from this formula that most of the mass is supported on the line where this is 0. So defined by alpha 1 equal to alpha 2. And then we were wondering whether this is just a coincidence for the constant kernel, but it turns out that this is quite robust property. So we studied the class of kernels bounded by power laws. So here, this is the L1 norm, is the sum of the components. So we have that case bounded from above and below by x to the gamma plus lambda, y to the minus lambda plus the symmetric. And for this class of kernels, first we show that, okay, there is a solution if and only if the parameters satisfy this condition. So to have just an idea, gamma and lambda are related with the coagulation between particles of similar size and particles of different size. And for these stationary solutions to exist, we need a balance between input and output. So this will require some condition on the coefficients, on the exponents. So for this class of kernels, there is a stationary solution, and we see that the solution will have the following property. So we study the limit of the solution over this dark region, AR, divided by the solution over this stripe, BR. And as R goes to infinity, this stripe is going to infinity. And also these two lines are shrinking towards this vector theta. And in the limit, we obtain that all the mass will be supported on the region defined by theta equal to the normalized vector. So this means that in the limit, all the particles will have a composition that is defined by the direction of the mass vector of the source normalized. So this theta is the mass vector of the source normalized. Eta is the source. This is a vector because this is a multidimensional integral. So integral of x1 eta, integral of x2 eta, etc. And the source defines then this vector eta, theta, which then defines the direction of localization in the composition space. So in the particle we see this not only in the stationary solutions of the coagulation equation with source, but also on the constant flux solutions. And we see even more because the localization happens not only asymptotically for large sizes, but everywhere for all sizes. So all constant flux solutions are supported on a one-dimensional line defined by theta 0. Where here theta 0 is the flux, is the vector flux normalized. And in terms of particles, what this means is that if I'm putting in the system as many red as green particles, then the large particles will have a composition that reflects this proportion. So just to give an idea of the proof, the idea is to rewrite the system into new variables in a way that we see the localization in the theta variable. So we have rho, that is the norm, L1 norm of x, and theta is x over norm of x. And so the localization will happen in the variable theta, which lives in the simplex. So we start by defining a probability measure on the simplex by means of this integral times, there is some moment here just to make sure that the integrals are finite, but it's not, it's just a technical detail. And then what we show is that by choosing an appropriate test function, we can show that this variable, we show that this double integral converges to 0, and this double integral is like a measure of the variability in the simplex, because when this goes to 0, we have the indication that the variability is decreasing. So this this will allow to prove that the as R goes to infinity, there is a family of Borel sets AR that are shrinking to theta 0, and such that the integral of the lambda R over AR is going to 1. So all the mass will be concentrated in AR, which is theta 0 in the limit. Okay. So I'm now going to show similar argument for the mass conserving solutions, just to see. So we start by writing obtaining existence of mass conserving solutions, and in this case we will need conditions on the exponents so that the mass is conserved, so to avoid the so-called gelation phenomenon, that is the formation of infinitely large particles in finite time. So we need that gamma, for example, is smaller than 1. And we can obtain existence of solutions by standard method, which I just put here the main steps. It consists in studying a problem for which we can show existence and uniqueness of solutions. So we truncate the gain term and the kernel in a way that the solution is compactly supported. Then Then the second step is to derive estimates uniform in R. And then using Velázquez, we obtain compactness of the family of functions, which allows to define the limiting function. And then the last step is to show that this limiting function satisfies the original equation. So this is quite a classical strategy in these equations. And what we can show in this for these solutions is that now there is no source. However, we also see some localization property, and at this time the localization is defined by the initial mass distribution over the different components. So if initially I have as many red particles as green, then for large times and large sizes, the particles will have a composition that reflects this proportion. So we obtain a similar result, but now we need to consider extra change of variable. So in fact, because the particles are growing and they grow at a speed which is a power of time, so most of the particles live in the so-called self-similar region. So then we have to do an extra change of variables. So we start with x, and we define the self-similar variable by this x over this power of time. And then we rewrite xi as in raw theta variables. And we study again the localization on the simplex in the theta variable. And so we have the following. Okay, so I just have to rewrite now everything in the new variables. So m0 is the initial total mass, so the integral of the norm of x f0. Theta 0 is the initial mass vector, normalized. And the conservation of mass tells us that, okay, the mass at time tau is equal to the mass initially. And we have the following result. There is a positive function delta, such that delta is going to 0, and this integral is converging to m0. So this integral is basically the mass over this region, theta minus theta 0, smaller than delta. And in the limit, this means that all the mass will be concentrated at the region theta equal to theta 0. Okay, so again, this is a similar idea to define a probability measure on the space of the simplex. So this is just the integral over A normalized. And then again, choosing a similar test function, we show that this double integral is bounded uniformly in M. We need an extra step here to get rid of the integration in time. So by showing that lambda m is continuous in time. And finally, this allows to show that there is a set of Borel sets, AM, that are shrinking to theta 0, and such that the integral of lambda m over am is going to 1 as tau goes to infinity. Yes. And Okay, just some final remarks. So, as we saw, localization can be seen as an emergent property because it holds for all kernels and it does not depend on the kernel. It depends on the source, in the case with source, and on the initial data in the case without source. It's universal, can be considered a universal property because it holds for many kernels. It allows to reduce multi-component to one-component systems. I will give an example in a minute. And then the next interesting question is how fast is the solution localizing? So how are the fluctuations along the line? And just to give an example of how this can be used to study the long time behavior for some particular class of kernels for which there is no explicit solution. So if we have this class of kernels that only depend on the data, so they are kernels that are constant along lines, then this localization result allows to, by combining with results from one component systems for the constant kernel, they allow to characterize completely the long time behavior of solutions of the multi-component equation. So this is a self-similar behavior, and there is a convergence towards a self-similar profile F0 that is a solution of the one-component equation. Okay, and this is it. So it would be interesting now to study this from the perspective of the particle system. So there are some results on the connection with the particle system from Norris, for example. And also it would be interesting to study what happens if we put fragmentation, or if we consider more general classes of kernels. Do we still have these properties or not? Yeah, this is all. Thank you.
So is there any question? Yes, please.
Yeah, so I'm a bit surprised because you wrote at some point that localization is not a property of the kernel. But it's not determined by the kernel, or?
Yes, exactly, because so it holds for all kernels in this class, and the direction of localization does not depend on the kernel. So if I
okay, but the important thing is that it's homogeneous, like with the same exponent in all variables.
Exactly.
The kernels that you are looking at is
yes,
basically
yes.
When you multiply them with the same number, you pull out and you have you always have the same exponent in all the variables.
Yes, all the different components. Yes.
Yes. So probably this is the reason why you get a straight line. And the direction is given either by initial condition or by the direction of injecting particles. So
in fact, we can have. So what is important is that the exponent is the same, but even if we have a kernel where there is like x1 plus 2x2, for example, since the exponent is the same, there is still localization. So even if there are twice as many collisions with particles of type 2 than particles of type 1, this doesn't matter.
Yeah. But probably,
the exponent is the thing that probably matters.
Yeah. So the follow-up question is, if I have different exponents, then probably, this is more of a question because the problem is maybe a little bit trickier, because the nice thing about the line is that it's basically invariant under the collision process. coagulation process.
Mhm.
But if you put like several exponents, maybe this would like gives for at least for large particles like some kind of drift. But then probably one has to take like some kind of convex combination or something. Or one has coagulation like kernels where larger particles coagulate even faster. So then probably you have localization around like not a straight line but some other lines. Do you think that these kind of things are true or?
Yeah, this would be very interesting to find out. But
I mean, I have the strong
Yeah,
feeling
I think
that this homogeneity of the kernel is really playing really the role how it behaves for large particles. But I don't
Yeah.
know if I have the right intuition.
That's, I think, a good question, so you can probably collaborate on that.
Yeah, sorry. The question I had was, at one point in your proof, you described a shrinking set of Borel sets that converge to, in a sense, to zero, and those the mass congregate there on these converging sets. I was wondering, is it just there exists, or do we actually build them? Do we know how they look? Is it for any set Borel set that goes to zero, you'll get the same result or a partial result, or is it more there exists due to a compactness argument?
it's more existence due to a compactness argument, so we don't know, for example, how fast it shrinks.
Mm-hmm. Do you think that if you have extra condition of regularity, you might be able to identify such sets, or is it more of, I think we're going to stick with the compactness for now?
I think this is probably because we have been thinking about that, and this is probably a matter of rescaling the solution in a way that in the limit we don't have like a Dirac, but some distribution. Yeah, and for this we need the speed of convergence. So yeah, probably it requires some different reformulation of the problem.
Okay, one final question.
Yeah, I'm just curious about the setting of the problem when you have a boundary condition. So you mentioned that it's possible to fix the flux. So is that still true for multi-component system? And how do you exactly fix the flux when you have a boundary condition?
So the flux. So for example, okay, no, so the flux is a vector. Here, for example, here. So this is a vector, and this is fixed. It's the how we fix the flux that is. This is a data given by in the problem.
Okay, so there's like some microscopic dynamic on that boundary that allows to fix the flux, or what happens exactly? What is like? I mean, I'm not curious how. I'm not familiar with this model, and I'm curious how does the boundary dynamic happen?
How it affects the system. So this represents like a flux of particles entering through zero size. Then the way that we can study it is by integrating the equation and having like a flux formulation of the equation, and then we study this equation where the flux is integrated. So then the mass is increasing in time. So they are basically solutions of this equation with mass increasing in time. instead of constant. Yeah.
Okay, thank you very much. So, now I run to